Hey guys, welcome back. So this is what I wanted to show you, and this is a just the insight into why we have to do the iterative calculations for the hub thickness. So we have to make some kind of assumption initially about the thickness that we think the hub needs to be. And then we do the calculation to find out that actually the hub thickness needs to be something else. Maybe it needs to be bigger, maybe it needs to be smaller. So we're basically just doing a trial and error set of calculations to find the ideal thickness. But you could also do this using Excel. So if you're familiar with doing calculations in Microsoft Excel, it's a great asset to you as an engineer because Microsoft Excel is probably the most used tool in any engineer's toolbox. Microsoft Excel is a powerful tool and very versatile. So I've set up this very basic calculation sheet where we enter the torque value that we have calculated for. We enter the assumed thickness, and it will calculate the force for us. And we enter the tensile strength of the material, so 8 megapascals, and it will calculate the ideal thickness and give us a factor of safety. And the reason that we have to do that iterative calculation process is to narrow in on the ideal hub thickness. So in our example previously, I said, let's assume that the thickness is 16 millimeters. So 0.016 meters. If I enter that, click OK, the calculation tells me that the ideal hub thickness is 29 millimeters based on that force. But the factor of safety, if I were to use this thickness, is 0.5, which means it will fail. So I know that my thickness has to be greater than 26, and it has to be closer to 29. So now I can do the calculation again for something for a slightly larger thickness, let's say 17 millimeters. You can see the factor of safety increases slightly. Now let's try for 20 millimeters, 0.02. Factor of safety is increased even more. So it's getting safer and safer as I increase the thickness, increase this assumed thickness. Now let's say my assumed thickness is 25 millimeters. It tells me that the ideal hub thickness will be 26 millimeters, and the factor of safety will be 0.9, so almost 1. So I need to increase the thickness a little bit more. Let's go 0.026. It tells me that the ideal hub thickness is 0.026 as well, and the factor of safety is pretty much 1, almost 1. So doing these calculations, I now know that in order for my hub to be safe, the thickness has to be greater than 26 millimeters. Because at 26 millimeters, my working stress is equal to my yield stress. You get me? So right now, at 26 millimeters, my factor of safety is 1. Now let's go back to our sheet given to us for our assignment. And let's look at this table here on the last page. It gives us factors of safety for elementary design work. And these are the different factors of safety depending on the situation. And you'll see here that factor of safety of 1.25 to 1.5 is for when we have a very reliable material and the conditions are very predictable, basically. And as the conditions get less predictable, the factor of safety increases, which is what we would expect. Now, as it is, our cast iron is a very predictable material, and we know with some certainty the types of forces that we'll be experiencing. So our ideal factor of safety will be 1.25 to 1.5. Okay, so keeping that in mind, let's go back to our calculation sheet. we need to make our factor of safety 1.25. So let's keep increasing this assumed thickness until we get close to that factor of safety. Let's go 0.028, 1.09. Okay, getting closer. Let's try 0.03. Factor of safety 1.2. So we're almost there. We need to make it just a little bit thicker. 0.031. Now at 0.031 or 31 millimeters, our factor of safety comes to 1.26 or 1.25.7, which falls within that category given by that table. So that was the purpose of putting that table in the assignment question, because we go back and forth until we get a factor of safety of 1.27. Right, you don't have to do it using this calculation sheet. You can do it all by hand if you want. But using Excel, it makes it a lot shorter and easier for you to see. So if you're interested in how to calculate for the factor of safety, the equation is the yield stress divided by your force divided by your assumed thickness times your key length, 0.055 or 55 millimeters. So that's how you would, that's the equation that you would use to find your factor of safety. And at the end of this whole thing, we now know that our ideal thickness is 31 millimeters. So hub thickness, 31 millimeters. And once you settle on an ideal hub thickness, that's the end of your hub analysis. Now remember, this hub thickness is not your hub diameter. Your hub thickness is just this bit. So your hub diameter is your your hub radius. Let's talk about hub radius before we do hub diameter. Your hub radius is your shaft radius plus half key length, half key height, sorry, plus hub thickness. So hub diameter is hub radius times 2. That's how you get your hub diameter. And this hub diameter you will use in your flange equation as well as in your bolt analysis. All right. So I won't talk about the flange analysis or the web analysis because the web analysis is very simple. I'll talk about the bolt analysis now. Is that okay with you guys? Okay, great. Right, so the first step when we do our bolt analysis is we have to find the PCD, or the pitch circle diameter. And the PCD is basically the distance from the bolt holes on one side to the center of the bolt holes on the other side. It creates a circle like this. So that's your circle diameter, pitch circle radius, or pitch circle diameter, sorry. Now, this hole in the middle here is supposed to represent your hub. So this is your hub outer diameter. So obviously our PCD will have to be greater than our hub diameter. And the PCD will equal your hub diameter plus 2 times whatever thickness or whatever distance you decide to identify from the center of the bolt to the edge of the hub. Let's call this distance A. 2 times A. Now this A is completely up to you guys. You guys have to be logical about this and decide what distance makes sense. Remember that distance there is to make sure that you can actually access the bolts using a wrench, using a spanner. You have to be able to get in there and tighten and loosen the bolts. So you have to come up with some realistic number or distance that we have to leave in order for our fitter to be able to tighten and loosen the bolts on this coupling. So if you say that you want to leave a distance of 50 millimeters, you bring that down here, and now it's just your PCD is your hub diameter plus 2 times 50, and that'll be your PCD. All right. Okay, once you have your PCD, you can go about solving either for your number of bolts or your size of bolts. Right, so there are two methods. We can either state the number of bolts and solve for size, or we can state the size and solve for number of bolts. And this will vary from group to group. Some groups might say that they want to use 5 bolts, but they don't know the size. And some groups might say that they want to use M12s, but they don't know how many M12s they have to use. All right. So you can do it either way. Now again, before you can jump into this, you have to first calculate the force that you'll be exerting. And your force is dependent on your PCD. So torque is equal to force times distance. So center of the shaft to the center of the bolt, that's the distance. The distance will be half of your PCD. So your force will be equal to your torque divided by PCD divided by 2. Right. Can anybody tell me the type of force that will be exerted here on these bolts? What type of force will these bolts be experiencing?
Shear stress.
Yes, a shear stress. So you have to look at this will be a shear force, so you'll be concentrating on the shear stress of the bolts. So shear stress, same formula as the normal stress or tensile stress. It's the force divided by the area. This force we've calculated here, and we'll plug it in here. The area will be the area of the bolts. So the bolts are circular in cross-section. They have a round cross-section. So the area of a circle is pi r squared times the number of bolts that you have. That's the total area. Shear stress. Now this shear stress, we will take it from information given in our assignment handout. Now if we go right back to the first page, it says here the tensile yield strength is 240 megapascals. Now we're interested in the shear strength, so we won't use this 240 directly. But if we then go and read the information about bolts, it says here the allowable shear strength of a steel fastener is about 0.6 times the tensile yield strength. So our shear strength that we will use here is 0.6 times our tensile strength, or 0.6 times 240 megapascals. This is the value that we will use in place of shear stress. And now this is where this statement comes in. You can either state the number of bolts. So you can either say if you want to use 5 bolts, you can either put in 5 here and then solve for R, or you could leave this as number of bolts and you could say that the radius is, let's say we're using an M12, so that's a 12 diameter. So the radius would be 0.0066 millimeters, and solve for B. So either one of these methods you can use. So let's say that we are doing it the other way and we're solving for the radius and we want to use 4 bolts. We plug all our values into the equation and we solve for R, and our R comes to about 5.5 millimeters. Let's just say, for example, which will mean our radius, or our diameter, is equal to 11 millimeters. And now using this information, we can go back to our data table for the sizes of bolts and look for M11. Now there's no M11, so the next logical choice will be M12. We can't go down, because if we go down, we'll be using a smaller diameter. Smaller diameter will mean the part will fail. So it has to be M12 or greater. So the size that we are going to go with is M12. And once you've done all this, then your final statement will be, after you've done the bolt analysis, you will use 4 by M12 at a PCD of whatever this distance is. And that's how you sum up or finish off your bolt analysis. All clear? Any questions? Any questions? Okay, if you have no questions, please leave your name and ID numbers in the chat so that I can take your attendance. Thank you very much for attending this afternoon, and I'll see you all next week.